Let's call this the grand finale of the talk on where the Earth and the solar system come from. So I've talked about things like chondrites and meteorites and nebular hypothesis, and I'm going to keep talking about that now. So let's move on to some more, in particular, some things about the terrestrial planets. So instead of talking, so previously I talked about the things like the giant planets, and how, if you remember, they're mostly made up of hydrogen and helium, gas and ice. But the terrestrial planets are made up of rock, just like Earth. And so Earth is, it's almost strange maybe to say that there are other planets that are terrestrial, right? If it's terrestrial, it's on Earth. If it's extraterrestrial, it's somewhere else, right? But so terrestrial here just means that it's made out of rock and has things like soil and sediment on its surface. So before, a few times, I had mentioned that we had the solar nebula. We built up the sun that had a nebular kind of composition, and the gas giants also have a nebular composition. When you remove most of the helium from the outer from the solar nebula, you're left with now it's still only a small proportion of it, but you're left with heavier elements like oxygen, iron, silicon, magnesium. And so those are all very common elements that are found in minerals and rocks on Earth: iron, oxygen, silicon, magnesium. Very, very common. So silicon and oxygen is what all the silicates have, and all the heavier mafic minerals have a lot of iron and magnesium in them. So these are very, in our experience, in our day-to-day experience, working with rocks, we see these elements all the time, right? But they're, again, only a tiny sliver of what the nebula in general is made up of. So how small are these things? Of a proportion are these things? So if you had 10 million marbles, 999,000, what is that? 9,999,900 of them would be whites, and then 100 left over would be of various colors. And of those marbles that have different colors, 35 of them would be green, 30 would be blue, 17 would be yellow, 12 red, 6 gray. Right. So this corresponds to what we have here for the chondritic composition. So people sometimes, when they look at this kind of figure, they think, oh, the nebula was made up of. They very quickly make this mistake that the nebula was made up of 35% oxygen. The majority was helium, but 35% was still that oxygen, right? Well, no, it's almost exclusively hydrogen and helium, right? So again, you have 10 million marbles, 35 of them are green. 10 million marbles, 35 of them are oxygen, right? I mean, if that was spread out in a field or pile in front of you, you would take forever. You would never even notice those 35 green marbles, or even these 100 marbles that are anything other than hydrogen and helium, right? So it's a very tiny percentage, and yet it's what makes up. It's enough to make everything that we know, right, on Earth, and that's ever been on Earth or ever will be on Earth and the other planets. So if we want to know how our solar system has changed over time, we look at the evolution of our terrestrial planets. And so all bodies in the inner solar system started out with that chondritic composition. Now we don't have samples of the planet at that early time, right? It's gone, or it's no longer available to be sampled, right? It's become what it is today. So how do we even know that it had this kind of composition? You could argue that it's theoretical, right? It's an implication of accretion theory, that the planets accreted from things like chondrites. But moving on from that, philosophical issue or actually valid scientific issue, we generally know that the planets formed from chondrites, and so it would have had a chondritic composition to start off with, right? But I said previously in the previous video here that they do not now have that chondritic composition, right? I mean, you take a sample of a rock or a sample of a mountain or the ocean floor, it's not going to have that chondritic composition, right? That 35, 35, 30, 17, 12, 6% composition. It's going to be vastly different, right? So on the one hand, this is obvious, right? Like I mean, I know I am not made up of that composition, and a lump of metal that I might have, any of the objects around me do not have that chondritic composition, because they are particular objects that have a very particular history, right? So it's not really meaningful to say that, well, I know that a car doesn't have a chondritic composition because it was made in a factory that doesn't build cars from chondrites, right? Technically, in the long term, that's how that car got here. It came here delivered as chondrites. Those are the original parts that it was manufactured from. So we're not talking about specific or individual objects in that sense. It's the planet as a whole does not have that chondritic composition, right? So you could have had a planet you could have a planet that still has a chondritic composition and has little things moving around on it, and they would have a very different kind of history than our planet had. So today the Earth does not have a chondritic composition, and so here's a sample of granite and a sample of basalt. Neither one of them have chondritic compositions, even though they started off as chondrites ultimately. So why is that? Because the planets have undergone differentiation. Earth has undergone differentiation, and the other planets have too. Some of the asteroid bodies that are large have potentially undergone differentiation, or have started differentiation and gone through part of it and not completed it. Okay, so what is differentiation? So today, the parts of the Earth are different than what they were in the past, right? They are different from each other. So the core of the Earth is mostly iron and nickel. One part is present as liquid, another part is present as a solid. The mantle of the Earth is not mostly liquid iron or nickel. It's made up of rock. It's very similar to a rock type called peridotite. And then the crust of the Earth is made up of rock, but it does not have the same chemical composition as the mantle. It has a different composition. And in fact, if you looked at the crust of the Earth, you'll see that some parts are very much like a sample of granite, and other parts are very much like a sample of basalt. So that would be the continents and the oceans, ocean floor anyway. So the Earth has many different parts. How did it get them? It started off as one kind of homogeneous piece that was all the same and was not different. So differentiation is the name we give to the process that resulted in this overall structure of the Earth, where you have metals and mantle and crust. And so differentiation is that process. The way that process occurred is through it was a density-driven process. So the things like iron and nickel are very dense, and in the molten early Earth, as chondrules and meteorites are crashing into it and vaporizing the surface and melting it, the things that are very heavy are able to sink to the bottom, and the parts that are lighter float to the top. So this is a process driven by density and things like buoyancy. The heavier materials sink; they are more dense and can go to the bottom. So, when we think of density or buoyancy, we think of boats on the water or something like that. But here we're talking about things that are dense enough to sink through molten rock. So people kind of have this idea. I know I used to when I was younger, that something falls into lava, it splashes and it sinks through it, and of course it's very hot, right? But the reality is, if you take something and throw it into a pool of lava, it's gonna splat on the surface and sit on the surface, and it can't sink because the lava is very dense. It has a density of a rock. And so just like people float a little more in very salty water, or float a little more in ocean water compared to fresh lake water, objects will have a very difficult time sinking through molten rock. It doesn't just give way, right? It's very dense. It's hard to sink through. So, but the core materials in the core, the iron and nickel, were able to sink through it. And the further down you go into the mantle, and closer you get to the core, the denser the materials, the denser are the materials. So even the minerals that are present at that boundary between the mantle and the core are rather different, very high density forms of the minerals that are present closer to the crust, far closer to the surface. So differentiation driven by density, right? It's just a sorting process. So meteorites, they tell us about differentiation in the early solar system too. So like, how do we even know that this happened on Earth, right? Well, we can see remains of planetary bodies that seem to be frozen in different steps of this process. And so when it was first found out, when these objects were first examined, it didn't make any sense, right? They were chondrites, and there were things that looked kind of like a chondrite if you took away all the metal, and then things that looked like what would be left if you took away from a chondrite everything but the metal. And then there are other objects that are like seem to come from that boundary between a metal core and a rocky mantle. That seems to actually record that particular boundary where you have solid metals and solid crystals mixed together perfectly, right? Not just little flecks of metal like in some earlier types of meteorites that we talked about that were just grouped together as clumps of dust and dirt, right? Actual molten metal with crystals embedded in it, crystals of rock. So there are some undifferentiated chondrites. There's some undifferentiated meteorites, and those are called chondrites. And then there are many differentiated meteorites. And perhaps a lot of them are chondrites that went through differentiation. And other ones might not be. They might be something completely different. So one of the first phases in differentiation is that the metals separate from the silicate minerals. And so we start with the chondritic composition, kind of nicely shown here. It might be hard to see in this video, but we have kind of a mesh of green and orange. So it's equally distributed. And then with melting and differentiation and this density-driven process, the metal goes to the core, and you have a core of metal and a wrapping of silicates. And so here we have an iron meteorite, and so that's probably almost always the core of an asteroid that went through differentiation. And then it collided with some other object and was destroyed down to its core. And pieces of the core flew off into space, and the ones that we have are the ones that actually end up hitting the Earth eventually. So density is mass over volume. It's the amount of mass that you fit into a volume, into a space. It has units, so units of mass are grams. The units of volume are cubic centimeters. So density is grams per cubic centimeter. And the density of water is set to 1 gram per cubic centimeter in the metric system. This is like a trick that the French played on everybody. They said water will be what we set everything else to. So we'll make water have a density of 1. Right? And then everything else follows from that. The density of most metals is 8 to 9 grams per cubic centimeter. The density of silicate minerals, it's a range depending on the mineral and the conditions it's under, but it can be from 2 to 4 grams per cubic centimeter. So right away you can see that these have very different densities, and just like a rock will sink in water or a block of metal will sink in water, these heavy metals will sink through a fluid of silicates, of molten silicates. And so I said before, you just throw someone or something onto a pool of lava, it doesn't sink. But if you throw metal into that pool of lava, it should sink. It's dense enough to start sinking. Everything else is going to float though. So this is kind of a goofy analogy here, right? But so we have ice cream that has things like cherries and nuts in it, right? And so it's mostly ice cream, and then it has mostly ice cream and has a little bit of cherries and nuts in it. And if it melts in your fridge, those components can separate, right? And so the ice cream is pretty low density, and then the nuts are lowest density, and the cherries, maybe they have like the stones still in them or something. That'd be a horrible ice cream, right? The pits in them are denser, right? And so it melts, and the nuts float to the surface. The cherries sink to the bottom, and you take a scoop, and you only get mostly nuts. And by the end of this ice cream, you get to the bottom, and it's almost all a scoop of cherries. So we used to get this kind of Italian ice at stores where you had to peel the top off, if you've ever had those. And when you'd eat them, by the time you got to the bottom, there would be a layer of crystal sugar, right? And that was the part that you really wanted. But so I think something similar was happening there. The sugar and ice maybe melted at some point, and they separated. And so your little cup of ice cream or Italian ice has gone through differentiation just like the planets or something. But so you can kind of relate to that, I think. So now the next step in differentiation doesn't just stop with the formation of the core, but maybe it does. Maybe a planetary body gets hit by an asteroid and is destroyed and is frozen in that point, right? But if it continues, at least how it did on Earth, those silicates that we have can separate into silicates that are very dense and silicates that are less dense. Right, the denser ones will sink, and the lighter silicate minerals, different types of crystal minerals, will float to the surface. And so the ones that sink, that are denser, they probably have denser elements in them, denser atoms. So the ones that float might have a lot of silicon and oxygen. And the ones that have sunk might have a lot of iron and magnesium. So most of the iron goes to the core and forms a metal core, but not all of it, right? It doesn't work perfectly, just like, in our Italian ice or ice cream analogy. Not everything gets totally separated completely, right? And there's potentially lots of processes going on, like overturning of this molten mass, or impacts that then stir it all back up, that can affect the distribution of these elements. And so you don't have all of the iron go to the core. So a lot of minerals have a lot of iron in them, and they're denser. And so we call those kind of minerals ultramafic minerals. And the lighter minerals might make up something like a basalt crust. So we can form two very different, an object with three different layers now, with the denser silicates and the lighter silicates. And so this picture here shows a meteorite that has, so it shows a meteorite and it shows the crystal minerals that are within it. And when a petrologist or a mineralogist looks at this figure under their microscope, this object under their microscope, they can identify the individual minerals. And they might say, this section, this object, has a lot of ultramafic minerals. Almost all the minerals are ultramafic, right? Iron and magnesium bearing minerals. And then when you couple that with the fact that it's a meteorite, there's the potential that this meteorite then is actually the remain of not just any part of an asteroid, but the mantle of an asteroid. So an asteroid that was able to go through at least this second step of differentiation. So now, there's a lot of possibilities here. You have this meteorite that represents the mantle of an asteroid. You can now examine its chemistry more. You can look at the types of weathering that have happened to the minerals that are present, and you can maybe see if there's any difference in the minerals there than the minerals that we see in samples of the mantle from Earth, which are very hard to get to. In fact, so it is hard to get samples of Earth's mantle. We can't drill down to it or anything like that at all. And so this is one of the ways we can kind of understand our own mantle and how it's behaved and changes over time. It's an analog or proxy for our mantle, which could be important for a lot of different reasons. Okay, and so now here you have a meteorite that looks like a piece of basalt when you do a similar process and look at the minerals that are present. And so this is possibly the crust of an asteroid that was hit and destroyed, or at least part of it was blown off and ends up landing on Earth. So now, just like the density of the iron and of the metals was different than the density of just silicate minerals in general, the density of different minerals can vary. So basalt, on average, basalt is a rock made up of different minerals, and on average, the density of those minerals is 2.7 to 3.0 grams per cubic centimeter. And for the minerals in an ultramafic rock, the densities are things like have a range of 3.2 to 3.3 grams per cubic centimeter. So it's still enough that if you put them together in liquid form, they're going to sink. They're going to separate based on density. And so now so here we have a type of asteroid called a palisite, and it's hard to see here, but what you have here is molten metal, or not molten metal, but it's metal that's that at one point was molten and became solid, and trapped within it are these green globs, and these green globs are very clear but still green crystals of things like olivine, and so you have a mixture of metal and rock, and because it's because it's obvious that the metal came from a melt, we know that it was melted, right? So it wasn't just little bits and pieces of metal that were captured by it. So this type of meteorite called a palisite is potentially the sampling the boundary between the core and the mantle of a planetary body, right? Of at least of a minor planet. And so now we can't get samples of the mantle. We surely, cannot get samples of the mantle core boundary, right? Sometimes we get some rocks that we believe came from the mantle and erupted to the surface. They were carried to the surface as they formed in the mantle as solid rock, and then were carried to the surface without melting. So that's a sample of the mantle, right? We get lava erupting from deep in the mantle all the time, perhaps, but it's molten, and so it's not really the same as the minerals that are present at the in the mantle itself. But so we have enough trouble getting that. There's no way we're getting this core mantle boundary. We can't drill anywhere near that. We can't drill into the mantle, let alone through it. So this is our way of understanding what's happening at that core mantle boundary. And, that's important because, for lots of reasons, right? But you might have seen in the news that Earth's magnetic poles are kind of moving. We think that that processes within the mantle and core are what affect the movement of the drift of the magnetic poles. And so the poles are actually moving, at least earlier this year, were moving very rapidly, much more rapidly than was expected. How do we model, the movement of the spinning core within the mantle? Well, we need to know what the properties of the materials that are down there are. So we need to look at meteorites like this. We need to look at these materials and try to, understand how they can behave under different conditions. So now step 3 of differentiation is that the crust and mantle continue to melt and differentiate even more. So in other words, we can get different kinds of crust. So today we find at the bottom of the oceans basalt, and so we have basaltic oceanic crust. And then on dry lands, we find something kind of like granite. It's on average like granite. If you look at one place or another, it's not granite. But if you look at them all together, it's kind of like a chunk of granite. And so that's continental crust. And those two are different. They have granite on average has a density of 2.6 grams per cubic centimeter. Basalt on average has a density of 2.8 to 3.0 grams per cubic centimeter. So we don't necessarily see basalt melting, settling through molten granite or anything like that. But when tectonic plates are starting to meet, potentially one part of the plate could be basaltic, another part could be granitic, and the more dense part can sink. If they have equal density, they might have to build up, and there's all kinds of things that can happen. But so this density-driven process is still happening even on the surface of the Earth, even within the crust. So when you look at all these objects now, the different types of meteorites and things like the Earth, Moon, and Mars, we can see that they have different amounts of differentiation, and then we can start grouping them as in order of increasing differentiation. So chondrites are undifferentiated. We have lots of different meteorites that show different stages of differentiation. The Moon is less differentiated than Mars. Mars is a little bit less differentiated than the Earth. We know these things because we have some samples from these bodies. We've sent people to the Moon. Earth has been hit by meteorites that broke off of Mars and landed on Earth. So we do have some samples of this, and we do have instruments that can, like geophysical instruments that can look at the interiors of these, or at least get information about the interiors of these planets. So we have some idea about the amount of differentiation within them. And then Earth is fully differentiated, right? Perhaps theoretically, there's more types of differentiation that could have happened, beyond what we have on Earth. So why do we see that though? Why do we see bodies with different amounts of differentiation, right? So when you group these objects according to their differentiation, you will then notice that they are also now grouped according to size. Chondrites are small, so chondrules are very small, millimeter size, but the the chondrite meteorites, so meteorites are kind of weird because in terms of the wording of this, you can have a large asteroid that gets hit and parts of it break off and form lots of little meteorites. So we call that original body the parent body that brought about the smaller meteorites. And so the parent bodies don't land on Earth, thankfully, right? Because they're very large and can cause big impacts. But so the parent body, what we get are the small broken off chips of different parent bodies. The parent body of the chondrites is relatively small compared to the differentiated asteroids, which are much larger, right? And the moon is even larger, and Mars is larger, and then the Earth is larger still. So what's going on here? So the larger bodies are able to hold their heat longer. They have more heat because they're much larger. And it takes a much longer time for them to cool off. It takes longer for them to lose their heat. And so as long as the body is hot and the material is relatively molten, you can have things sinking and floating within it. But once you freeze it, or once it cools off, then there's no more of this differentiation, right? So it's kind of like almost the reverse of that ice cream example. If you melt that ice cream and then start stirring it up, the cherries and nuts and ice cream are all going to be nicely distributed. And then if you pull out the stirring, they're going to start separating. But then if they suddenly freeze, they might not be have separated enough to have different distinct layers. So things like Earth still has a molten mantle. Earth can still go through differentiation. Mars is thought to have had a molten mantle, and so molten mantles are related to plate tectonics, and so Mars may have had its own style of tectonics, but then it lost its heat and that process stopped. So Mars is kind of a dead planet. Earth is considered to be a living planet still, not because of the animals living on it, but the rocky body of the planet itself is still active. And so Earth is cooling, and I said before perhaps there's other theoretical stages of differentiation, but probably not, because Earth is still has this molten mantle. If there's more to differentiate, it could be differentiating right now, or it would have already differentiated. So there's probably not much beyond what you see on Earth in terms of differentiation. But who knows? We don't know too much about planets outside of our solar system, right? At least not in this kind of detail. But we do know, because we can see things like differentiation happen on Earth and Mars and all of these different meteorites, that the same process is going to exist on other solar systems, on other star systems. So we know that there are other planets. We've seen lots of them. When I was a college student, there were none. And our professors were telling us one day there's going to be thousands of planets out there. It's going to start with just a few, and before long, it's going to be thousands of different planets that everyone knows about. And yes, here we are at that point, where there are many extrasolar planets. And so we know through geology, right, not necessarily through astrophysics, some of the things that have happened in those solar systems. We know about the formation of chondrites and chondrules forming chondrites. Those other planets almost certainly started off in a nebula with a nebular composition, and when things cooled there, they likely went through the same processes that happened in our nebula, forming chondrites. And so the rocky planets, we can expect that there are rocky planets in these other solar systems, and we sometimes know that there are. We've observed some. Most of the early planets that we observed in other solar systems were gas giants, obviously, because they're easier to see. But we expect that when you have a nebula, you're going to have that tiny little bit of dust and rock, and it's going to form terrestrial planets that are Earth-like, right? Okay, so that was kind of a digression, I guess. But when we also look at, when we arrange these differentiated objects, we can also see something about the age of them. So the chondrites are extremely old. They're as old as the solar system, basically. The object, our date for the age of the solar system is derived from an experiment on chondrites. Right? It is a chondritic age. And so they're very old. The differentiated meteorites are younger, and things like the moon and Mars are even younger and younger. And that's because Earth has an age of 0 because it's still active. It hasn't been frozen and stopped and had its clock stopped. It's still changing. It's still an open system undergoing change, whereas the chondrites are not. So Earth is still geologically active and still evolving, and lots of different processes are happening on Earth. Just anytime you look at a picture of the Earth, even though this one has Antarctica in the top, you can see some of these processes. So we've talked a lot about some of the mantle and formation processes, but there's interactions between the atmosphere, the ocean, land, and everything else on the planet. So we'll talk more about those kinds of things too. Okay. So I think I'll end this talk here with this reminder again that Earth is still geologically active and evolving.